Right then, hello, welcome back. Today I want to look at square waves and how they're comprised of, infinite, well, a perfect square wave would be comprised of infinite odd harmonics, a sum of infinite odd harmonics. And today I want to look at that and how we can program that into Desmos and create a square wave with with increasing numbers of harmonics. Okay, so here on Wikipedia, I've got the Fourier analysis. Now, if you've ever done any digital communication studies, you might have come across this. It's in our interest to send the best square waves we can down communication channels, direct switches between ones and zeros. But as with everything in engineering, there are offsets, engineering compromises we have to make about signal quality and the expense of the medium we're sending these signals down. So let's take a look at this. I've got the sine of 2 pi ft, but 2k minus 1 is a mathematical sequence, and it's actually, if k is an integer, this will give me odd numbers. Yeah, so when k is 1, this bracket will become 1, and when k is 2, this bracket will become 2 times 2 is 4 minus 1 is 3. On and on, so we get 1, 3, 5, 7, 9, and that'll be the odd harmonics of a frequency. And the denominator here is the same thing, but as each harmonic increases, the amplitude of each harmonic will reduce by, well, a third each time. So the first harmonic will be a full wave with amplitude 1. The next one will have amplitude a third, then a fifth, then a seventh. So the amplitudes diminish as the frequencies increase. And if you keep going to infinity there, the end top of that sigma sign, you'd end up with a perfect square wave, but obviously we can't get to infinity. So we can never get a perfect square wave using this Fourier sum. Okay, let's go to Desmos and take a look how to do it. So we're going to start off with y equals, and I want my sum function. I'm going to start at sum equals 1, and for the time being, I'm going to just use 5 harmonics. Now I want sine divided by, well, I can do the bottom part, 2n minus 1. That was from before. And for sine, I'm going to want 2n minus 1 in there. Oops. With x here, but I really want all that in brackets. So you can see if I have, at the first 5 odd harmonics, I get quite a, starting to look like a square wave. If I add fewer harmonics, it looks less like a square wave. And I can keep increasing them and we get closer and closer. Now, you can see the amplitude of this one's not quite 1. To make it 1, we need to multiply the whole thing by 4 over pi. There you go, that puts the amplitude at 1. And rather than having that set to some hard number, I'm going to put a variable in and just let it slide between 1 and, I don't know, let's say 10. And so you can start off when we've got no harmonics there. When A's at 1, we just get the first fundamental harmonic. Now let's press play. And as you can see, that sliding bar is just adding more and more harmonics. So as it increases up to 10, we get closer and closer to a square wave. Now, obviously, I can increase this upper limit. Let's go to 50. And you can see as it gets much, much closer. Let's increase the speed. So as it adds more and more harmonics, it gets closer and closer to a square wave, but you can see it never quite actually gets to a perfect square wave. We've got these overshoots as well. Now there's something I remember my teacher telling me during my apprenticeship, something called the Heaviside function, which will eliminate those overshoots, but something we're stuck with for now. So, gives you an idea how to program a square wave function at Desmos. And why am I talking about this? Well, one of the other videos we talked about bandwidth, so I made some notes here. We've got the sine of 2n minus 1x. Now that's supposed to represent omega t. Now omega is angular velocity. It can also be represented as 2 pi times frequency. That's another way to represent omega, angular velocity, 2 pi f. So 2 pi ft. We can see there that 2 and pi are constants. So when I'm increasing n in that sum here, it just relates to a direct increase in frequency. So an increase in n means an increase in frequency. Now, as communication engineers, we want to have the cleanest signals we can have. And to have the cleanest signal, we need to have the best square waves we can possibly have. Now, to have the best square waves, we need to use the most frequency harmonics we can possibly use. But when we do that, we're increasing the bandwidth we need to use. And when you increase the bandwidth, you're going to have to use a more expensive medium of communication. So, i.e., you might have to use fiber optic instead of coax. And like everything in engineering, better bandwidth, more expensive medium. So that there's always compromises to be made. Okay, I hope that helps anybody. I always like to, in my old jobs, I used to like putting this into the computer and just watching at it catatonically. I find it therapeutic to watch things like this, but there you go, that's me.